Imagine a world beyond our senses, a world where our everyday notions of space and time cease to hold true. In this realm, the very fabric of reality is woven from threads that defy our conventional understanding. This is the captivating realm of quantum mechanics, a field that has intrigued and baffled scientists for over a century. Here, the rules of classical physics are turned on their head, and particles behave in ways that seem almost magical, where particles can be in multiple places at once, and reality is determined by chance. This phenomenon, known as superposition, challenges our very perception of existence. For decades, physicists have been grappling with the mind-boggling implications of this theory, debating its meaning and conducting experiments to test its predictions. The journey has been long and arduous, filled with moments of both triumph and frustration, pushing the boundaries of our understanding of the universe. Each discovery brings us one step closer to unraveling the mysteries of the quantum world, a world that operates on principles vastly different from our own. Recently, a groundbreaking experiment has propelled us further into this mysterious domain, shedding new light on the enigmatic nature of quantum mechanics. This experiment has opened doors to possibilities that were once thought to be purely theoretical, offering a glimpse into the enigmatic realm of higher dimensions. These dimensions, beyond the three spatial dimensions we are familiar with, hold the key to understanding the true nature of the universe. Scientists have conducted an experiment that delves into the depths of the 37th dimension, a concept that sounds like something straight out of science fiction, but holds profound implications for our understanding of the cosmos. This exploration into higher dimensions could revolutionize the way we perceive reality. A concept that sounds like something straight out of science fiction, but holds profound implications for our understanding of the cosmos. By venturing into these uncharted territories, we are not only expanding our knowledge but also challenging the very foundations of physics. This groundbreaking research opens a Pandora's box of possibilities, revealing new pathways for scientific inquiry and technological innovation. The implications of these discoveries are vast and far-reaching, touching on everything from the nature of consciousness to the potential for new forms of energy. Challenging our preconceived notions of reality and pushing the boundaries of human knowledge. As we delve deeper into the quantum realm, we are forced to rethink our understanding of the universe and our place within it. Join us on a journey to explore the intricacies of this experiment and uncover the secrets it reveals about the very fabric of our universe. This journey is not just for scientists, it is for anyone who has ever looked up at the stars and wondered about the mysteries of existence. This is not just an abstract mathematical exercise. It is a quest to understand the fundamental nature of reality. The insights gained from this research have the potential to transform our world in ways we can scarcely imagine. It has the potential to revolutionize our understanding of the universe and pave the way for technological advancements beyond our wildest dreams. The future is full of possibilities, and the journey has only just begun. To comprehend the significance of the 37th dimension experiment, we must first delve into the fascinating world of quantum mechanics. This realm, often described as the foundation of modern physics, is where the smallest particles of the universe reveal their secrets. It's a world that challenges our understanding and stretches the limits of our imagination. In the early 20th century, physicists discovered that the laws governing the macroscopic world break down at the subatomic level. This was a revolutionary period, marked by groundbreaking experiments and theories that reshaped our view of reality. Figures like Niels Bohr, Albert Einstein, and Werner Heisenberg were at the forefront, exploring the mysteries of atoms and their components. Particles like electrons and photons behave in ways that defy common sense, exhibiting both wave-like and particle-like properties simultaneously. This duality is famously illustrated by the double-slit experiment, where particles create an interference pattern, a hallmark of wave behavior, even when fired one at a time. Such phenomena challenge our classical intuitions and force us to rethink the nature of matter and energy. One of the most bizarre aspects of quantum mechanics is the concept of superposition, which states that a particle can exist in multiple states at once until it is observed. This idea is not just theoretical, it has been demonstrated in numerous experiments. Superposition is a cornerstone of quantum theory, leading to technologies like quantum computing, where bits can be in a state of 0, 1, or both simultaneously, vastly increasing computational power. Imagine a coin spinning in the air, neither heads nor tails until it lands. This analogy helps us grasp the essence of superposition, where outcomes are not determined until a measurement is made. In the quantum world, this means that particles exist in a state of probability, embodying multiple possibilities at once. Similarly, a quantum particle exists in a blurry haze of possibilities until a measurement is made, collapsing its wave function into a single state. This process, known as wave function collapse, is a fundamental aspect of quantum mechanics. It underscores the role of the observer in determining the state of a quantum system, a concept that has profound philosophical implications. This inherent uncertainty is not just a limitation of our measurement tools, it is a fundamental property of the quantum world. The Heisenberg uncertainty principle states that we cannot simultaneously know both the position and momentum of a particle with absolute precision. This principle highlights the intrinsic unpredictability of quantum systems, a stark contrast to the deterministic nature of classical physics. This probabilistic nature of reality has profound implications for our understanding of the universe, suggesting that the future is not predetermined, but rather a tapestry of possibilities. It opens up a realm where multiple outcomes can coexist, and the act of observation plays a crucial role in shaping reality. As we continue to explore the subatomic world, we uncover more about the fundamental nature of existence, pushing the boundaries of what we know and what we can imagine. Our everyday experience conditions us to perceive the world in three spatial dimensions: length, width, and height. These dimensions are the framework within which we navigate our daily lives, from the simplest tasks to the most complex engineering feats. However, theoretical physics, particularly string theory, suggests that our universe might be far more complex than we can perceive. This field of study opens up a realm of possibilities that challenge our conventional understanding of space and time. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but rather tiny vibrating strings. These strings vibrate at different frequencies, and their vibrations give rise to the particles and forces we observe. These strings exist in a multidimensional universe, with some theories suggesting as many as 10 or even 11 dimensions. These additional dimensions are essential for the mathematical consistency of string theory. These extra dimensions are not some far-off realms, but are thought to be curled up and compactified at incredibly small scales, far beyond our ability to observe directly. They are hidden from our senses, yet they play a crucial role in the fabric of the universe. The 37th dimension referred to in the experiment doesn't necessarily correlate to these spatial dimensions proposed by string theory. Instead, it represents a more abstract concept within a specific mathematical framework. Instead, it emerges from a specific mathematical framework used to describe the behavior of quantum particles. This framework allows scientists to explore the properties and interactions of particles in ways that transcend our everyday experience. It's a dimension in a more abstract mathematical space, representing a degree of freedom in the system, rather than a physical direction we can point to. This abstract space is a powerful tool for physicists, enabling them to make predictions and understand phenomena that would otherwise be beyond our reach. By delving into these higher dimensions, scientists hope to unlock new insights into the fundamental nature of reality. The exploration of the 37th dimension is just one example of how theoretical physics pushes the boundaries of our knowledge, challenging us to think beyond the limits of our perception. As we continue to explore these abstract dimensions, we may uncover new principles that govern the universe, leading to advancements in technology, new forms of energy, and a deeper understanding of the cosmos. The journey into the 37th dimension is a testament to human curiosity and the relentless pursuit of knowledge. Section 4. Constructing the experiment. A symphony of lasers and atoms. The experiment involved trapping a cloud of ultra-cold atoms in a lattice of crisscrossing laser beams, creating a synthetic crystal of light. This optical lattice serves as a highly controlled environment to simulate the behavior of electrons in a solid material. By precisely tuning the properties of the laser beams, researchers were able to manipulate the interactions between the atoms, effectively creating a system that mimics the behavior of particles in higher dimensions. This is analogous to creating a two-dimensional shadow of a three-dimensional object, allowing us to glean information about the higher dimensional object by studying its lower dimensional projection. The researchers then used a technique called quantum gas microscopy to observe the behavior of the atoms in the optical lattice. This technique allows them to track the movement and interactions of individual atoms with incredible precision. Section 5. Echoes from the 37th dimension. Observing the unobservable. By closely monitoring the atoms trapped in the optical lattice, the researchers observed a peculiar phenomenon. The atoms exhibited collective behavior that could only be explained by considering the system as existing in a higher dimensional space. Specifically, the patterns of entanglement and correlations between the atoms matched theoretical predictions for a system with 37 degrees of freedom. These echoes from the 37th dimension were not directly observable in our three-dimensional world, but manifested as subtle correlations in the behavior of the trapped atoms. Imagine a pond with ripples spreading outward from a dropped pebble. We cannot directly observe the pebble itself, but we can infer its presence and properties by studying the patterns of the ripples. Similarly, the researchers were able to infer the existence and influence of the 37th dimension by carefully analyzing the intricate dance of the atoms in their experiment.